Throughout the year, we discussed many unique properties of water. Another property is autoionization or self-ionization of water. I will explain more in detail in the next slide. The equilibrium constant for water, or ion product constant, is Kw. It is equal to 1.0 times 10 to the negative 14th at room temperature or 25 degrees Celsius. You must memorize this constant. I will not provide this constant for you. The water constant and any other temperature I will provide. Autoionization of water occurs because two water molecules get together and one of the water molecules behaves like a bronzyloric acid, the other one behaves like a bronzyloric base. So the bronzyloric acid will donate a hydrogen to the bronzyloric base to produce H3O+, which is a conjugate acid. These two are a conjugate pair, and the water's conjugate pair will be hydroxide ion, which is my conjugate base. They differ by one hydrogen. So we could write our equilibrium constant. General formula for equilibrium constant is K is equal to products over reactants. My products are H3O+ and OH-. We don't have any reactants because these are both in the liquid state. And remember, Kw is equal to 1.0 times 10 to the negative 14th at room temperature. Since water autoionizes into H+ or H3O+ and OH-, we could compare the concentration of H+ to OH-. When the concentration of H+ is greater than OH-, the solution is acidic. Therefore, the pH has to be less than 7, while the pOH must be greater than 7. When the concentration of H+ and OH- are equal to each other, this is neutral. pH and pOH will equal to 7 for both. If it's basic, the H+ concentration is less than the OH- concentration, so the pH is greater than 7 and the pOH is less than 7. You have seen H3O+ many times. H3O+ is known as hydronium ion. It is the same thing as an H+ ion or a proton. A neutral hydrogen atom has one proton and one electron. When it becomes an ion, it loses an electron, which is the same thing as a proton. These three things, hydronium ion, H+ ion, and proton, all mean the same thing in this unit. pH and pOH calculations. pH is equal to the negative log of H+ concentration, or the hydronium ion concentration, H3O+. pOH is equal to the negative log of OH- concentration. P here stands for negative log. When I add pH plus pOH, it is equal to 14. Because Kw is equal to H+ concentration times OH- concentration. So Kw is equal to 1 times 10 to the negative 14th. This is equal to H+ concentration times OH- concentration. So I'm going to negative log both sides. So negative log of 1 times 10 to the negative 14th is going to equal to negative log of H+ times the negative log of OH-. The negative log of 1 times 10 to the negative 14 is 14. This is equal to negative log. To calculate multiplied logs, we must add them. So I rearrange this and this becomes log H+ plus negative log OH-. So if we look above, pH is equal to negative log of H+, pOH is equal to the negative log of OH-. So we could substitute that in. So 14 is equal to pH plus pOH. This is how we get this above equation here. Significant digits for pH and pOH are different. The significant digit starts after the decimal. If we have something like 5.301, this number has 3 significant digits because it must start after the decimal. 301 is my significant digit. So for pH and pOH, significant digit starts after the decimal. Pause the video, complete this table, and then check your answer. To find the pH is equal to negative log of H plus concentration. So this is going to be pH is equal to negative log of 3.89 times 10 to the negative 4. So plugging it into the calculator, you just go from left to right, negative log 3.89 times 10 to the negative 4th, and you should get 3.41005. So now we have to do sig figs. This original number has 3 sig figs because this is not pH or pOH. We ignore the exponent. Everything in the front is significant. So I need 3 in my answer. For pH and pOH, sig figs start after the decimal. So 4 is my first sig fig. So 1, 2, 3. I look 1 to the right. So it stays is. So my answer is 3.410. pOH, there are 2 ways you could solve for this. The easiest way to solve for this is pH plus pOH equals 14. So my pH is 3.410 plus pOH is equal to 14. So this becomes 10.590 with correct sig fig. To find the OH minus concentration, again, there's 2 ways. You could use the KW equation or pOH. I'm going to use KW here. So KW is equal to H plus times OH minus. So KW is 1 times 10 to the negative 14. This is equal to 3.89 times 10 to the negative 4 times OH minus. So if I do my math correctly, is 2.5709 times 10 to the negative 11th. And there's 3 sig figs. Count from the beginning. 1, 2, 3. I look 1 to the right. It stays as is. So my answer is 2.57 times 10 to the negative 11th molar. Concentration have units of molar or moles per liter. pH and pOH, since we are taking the log, are unitless. To calculate the pH, we're going to use pH plus pOH is equal to 14. pH plus 5.19 is equal to 14. So this becomes 8.81 with correct sig figs. There are 2 after the decimal. There are 2 after the decimal. To calculate for H plus, we're going to use pH is equal to negative log of H plus concentration. So pH is equal to 8.81 equals to negative log of H plus. So the first thing I need to do is divide both sides by negative. So this becomes negative 8.81 equals to log of H plus. And we need to do the anti-log. So when you do the anti-log, you can type in second log in most calculators. And you'll get something like this as your display. And you type in negative 8.81. So if you punch this into the calculator correctly, you should get 1.5488 times 10 to the negative 9th. This has 2 sig figs. I need 2 in my answer. Since this is not pH or pOH, we count sig figs as we did before. So 1, 2, 1 to the right. The 5 stays. So this becomes 1.5, negative 9. And since this is concentration, it has units of molar. The OH minus, you could use pOH to solve for it, or you could use KW, either or. It won't make a difference. If I use KW, KW is equal to H plus OH minus. This becomes 1 times 10 to the negative 14th equals to H plus, which we calculate as 1.5 times 10 to the negative 9th times OH minus. So OH becomes 6.456 times 10 to the negative 6. I need 2 sig figs, so 1, 2, I look 1 to the right, goes up. So this is 6.5 times 10 to the negative 6 molar. For the next one, to find the H plus concentration, we have to use pH. So pH is equal to negative log of H plus. So pH is 8.46 equals to negative log of H plus. First thing you need to do is divide by a negative and then take the anti-log, and you should get 3.467 times 10 to the negative 9th. This one has two sig figs because for pH and pOH, the sig figs start after the decimal. So my final answer needs 2. So it's 1, 2. I look 1 to the right. So this becomes 3.5 times 10 to the negative 9 units of molar. To find pOH, the easiest way to do this is pH plus pOH is equal to 14. That's going to be 8.46 plus pOH equals to 14, 5.54. To find OH minus, we could use pOH. This is going to be negative log of OH minus. So this is going to be 5.54 equals to negative log of OH minus. So the first thing you're going to do is divide both sides by negative and then take the anti-log. And when you do the anti-log, you should get 2.88 times 10 to the negative 6. It needs 2 sig figs, so it's 1, 2. I like 1 to the right, so it's 2.9 times 10 to the negative 6 molar. It needs units. For the last one, I need to find pOH first because I have the OH minus concentration, or I could find the H plus concentration, either or. So the pOH is going to equal to negative log of OH minus. This is negative log of 2.31 times 10 to the negative 4th molar. This equals to 3.6364. My concentration has 3 sig figs. I need 3 sig figs in my pOH, which starts after the decimal. 1, 2, 3. I look 1 to the right, so it just stays as is. So my answer is 3.636. My H plus concentration, I have to use KW. It's equal to H plus times OH minus. KW, remember, is 1 times 10 to the negative 14. This is equal to H plus, what we're looking for. OH is 2.31 times 10 to the negative 4 molar. So the H plus concentration becomes 4.3290 times 10 to the negative 11th. Since this concentration is going to have 3 sig figs, so 1, 2, 3, I look 1 to the right, and so the 2 becomes a 3 times 10 to the negative 11, and this is in molar. My pH, add the pH plus pOH equals to 14, so pH plus 3.636 equals to 14. That's going to be 10.364. To determine if it's acidic, neutral, or basic, the easiest way to do this is look at your pH column, but you could look at your pOH or compare the H plus to OH minus concentration. You'll still get it correct. So if I look at pH for the first one, it is less than 7, so this is acidic. I could also look at my pOH. My pOH is greater than 7, so we know it's acidic. And if I compare my H and OH, my H plus is to the negative 4th, my OH minus is to the negative 11. So we know this is acidic, but it's easiest if you just compare the pH. For the second one is 8.81, so it is above 7, so this is basic. Third one is also above 7, so it is basic. And the last one is also above 7, so this is basic. If you notice, there is more than one way to solve for these problems. Pick one that works for you. The biggest issue here is you need to check for sig fig. pH and pOH start after the decimal. For concentration, H plus and OH minus, the sig figs are done as we did before. So here you want to find the pH of a 3.5 molar HI solution. So first of all, we need to write an equation. HI is a strong acid, so it's going to dissociate 100%. So that means if I start with HI, which is AQ because it's a strong acid, it is going to break down 100%. So it's going to break to H plus AQ and I minus AQ. Its conjugate is going to be weak. So we start with 3.5 molar solution. Since HI is a very strong acid, as the reaction proceeds to an end, there will be no more HI present. Only thing present is the ion, the H plus ion and the I minus ion, which is its conjugate base, because I minus and HI differ by 1 hydrogen. Since I started with 3.5 molar, if I dissociate this, I'm going to have 3.5 molar H plus and 3.5 molar I minus. The formula for pH is equal to negative log of H plus concentration. Since the HI broke down completely, the H plus in solution is all the hydrogen ion. So we could just plug in that number, which is negative log of 3.5 molar, which equals to, this becomes negative 0.544068. So counting for sig figs, 3.5 has 3 sig figs. Since it is not pH or pOH, we count sig figs as normal. In our answer, since it is pH, it starts after the decimal. So it's 1 to the right. So my answer is 0.54. pH and pOHs can have negative values. That just means that they're very acidic or very basic. Pause the video, try this problem on your own, and then check your answer. So what is the pOH of 1.00 molar of radium hydroxide solution? So RaOH2 again is a strong base. So it will dissociate 100% to Ra2 plus 2OH minus. You need to make sure balance your equation as well as your charges. These are all AQ. We start with 1.00 molar of radium hydroxide. At the end of the reaction, there is no radium hydroxide because it's a strong base. It would dissociate 100% into Ra2 plus and 2OH minus for every 1 radium hydroxide. Since it's a strong base and a strong acid, we do not do a double-headed arrow. We only do a single arrow because there is no reactant. If I start with 1.00 molar of radium hydroxide, when I break this down, I'm going to have 1.00 molar of Ra2 plus, but 2 times 1.00 molar of the hydroxide ion, because for every 1 radium hydroxide, there is 1 radium atom and 2 hydroxide atoms. So we need to balance that. We are looking for the pOH. So pOH is equal to negative log of OH minus concentration. Radium hydroxide dissociated 100%. That tells us that the OH minus concentration is all present in solution. So all I have to do is take the negative log of 2.00 molar to get negative 0.30102. Now I need to do sig figs. 1.00 has 3 sig figs, so I need 3 sig figs in the answer. Since this is pOH, it starts after the decimal, so 1, 2, 3. I look 1 to the right, it stays in, so negative 0.301. No units. Pause the video, try this on your own, and then check your answer. So we have H2SO4, which is also a strong acid, so we're going to dissociate that. So H2SO4, this is AQ, will break into 2H plus AQ plus SO4 2 minus AQ. We start with 0.15 molar of sulfuric acid, but since this is a strong acid, by the end of the reaction there will be no H2SO4 present. However, there will be 2 times 0.15 molar of hydrogen ion, because for every H2SO4 I break down, there's always 2 H pluses and 1 SO4 minus. So we are looking for the pOH, and there are 2 ways we could solve for this. We could use KW if we wanted to, And if I use Kw, this is going to equal to H plus OH minus. Kw is equal to 1 times 10 to the negative 14. This is equal to H plus, which is 0.30, which is 2 times 0.15 molar, times OH minus. So OH minus equals to 3.33 times 10 to the negative 14. Working on sig figs, this is a constant, does not count. My 0.15 has 2. My 0.30 has 2, so I need 2 in my answer. 1, 2. I look 1 to right, so this is 3.3 times 10 to the negative 14 units of molar. Remember, concentration always has units of molar. pH and pOH do not. Pause the video, try this problem on your own, and then check your answer. What is the H3O plus concentration of calcium hydroxide solution with a pOH of 13.731? First thing we do is rewrite an equation. Since calcium hydroxide is a strong base, it's going to dissociate 100%. So calcium hydroxide, AQ, will break into Ca2 plus AQ plus 2 OH minus AQ. So pOH is equal to negative log of OH minus. We can find the OH concentration because we know pOH is 13.731. This is equal to negative log of OH minus. Divide both sides by negative first, then take the anti-log, and you should get OH minus to equals to 1.8578 times 10 to the negative 14th molar. We need to find the H3O plus concentration. So Kw is equal to H3O plus times OH minus. This is 1 times 10 to the negative 14th. This is equal to H3O plus times 1.8578 times 10 to the negative 14th molar. So H3O plus equals to 0.53826. So now I need to do sig figs. Sig figs for pOH start after the decimal, so there's 3 here. So I need 3 in the answer. So I go to the first non-zero digit, which is a 5. 1, 2, 3. Look 1 to right. The 8 stays, so 0.538 molar. There are many ways to solve for pH and pOH. Sometimes you could use pH plus pOH is equal to 14. Sometimes you will use Kw is equal to H plus concentration times OH minus concentration. Just plug in the numbers correctly. All strong acids and bases dissociate 100%. Equilibrium lies on the weaker side. So in this case, that is the product side. This is why when we write an equation with strong acid and bases, the arrow goes only in one direction. Be careful with your significant digits. pH and pOH starts after the decimal. They have no units, so they are unitless. Concentrations, the sig figs are done as we did before, and they have units of molar or moles per liter.